Okay, so again, here we go. We finished this problem right before we left. And so we're down to just a handful of slides on this day 5 special topic stuff. The major thing to remember is this. Your electron configuration and your amount of energy can be tied together. Remember, we started over here with the 1s2, then we moved the 2s2, 2p6. All of that can be tied into this portion right here. And you can see that as we move across, the energy decreases. That's because things like magnets, they're getting further away from the pulling power, so it's easier to rip them apart. Okay? They decrease a little bit, not too much. Now we get to this. Another example problem here, it says we have ozone's being depleted, shown in this particular equation. And as the UV ultraviolet radiation strikes the ozone, it actually absorbs or blocks the harmful stuff from the UV light from the sun. And we have a couple of things here. It says a molecule of O3 absorbs a photon, which we can kind of explain here a bit, with a frequency of 1 × 10 to the 15th inverse seconds there, or hertz. How much energy in joules does the ozone molecule absorb per photon? So there's two equations that we have to be aware of to solve this problem. Number one was the speed of light formula, which we started out with C. Does anybody remember C equals what times what? There we go. Wavelength times frequency. And then I'm going to put another equation here in a different color. RE for energy equals, anybody remember? There it is. H for Planck's constant times that frequency again. Okay, so that's how we tie both of those things together. So that ozone absorbs something with a frequency of 1 × 10 to the 15th hertz, or inverse seconds there. We want to know how much energy to use. So do we even have to, in this first part, worry about the speed of light formula? No, because we're already given frequency and we can jump right into that. And so we can say, all right, down here, our E for energy equals our Planck's constant, which, does anybody remember that off the top of their head? Yep, 6.626 times 10 to the negative 34 joule seconds times that frequency that's given at 1.00 times 10 to the 15th hertz. Okay, so all we got to do is plug this into our equation, and voila, we'll pop out a value for our value of energy. So 6.626 times 10 to the negative 34th times 1 times 10 to the 15th, and I get 6.63 times 10 to the negative 19th joules. Okay. All right. Then it says the minimum energy needed to break that oxygen-oxygen bond in ozone is 387 kilojoules per mole. Does a photon with the frequency that we have seen here have enough energy to break the bond? Support our answer with our calculation. So the first thing, I'm just going to reorientate this value here of 387 kilojoules per mole into a more realistic format here. So what I like to do is this. I like to say, all right, 387 kilojoules, and then I'm going to draw it like this, per mole of our ozone, okay? And we want to break this ozone down into its individual pieces or part. So what we have to do here is this. We have to think about okay, how can we take or relate this 387 number to what we already have up here? Okay, so here we go with this. This energy is per one piece or part. And so if we do this, and this is how the book does it, and I probably should have just started with that. So I'm going to erase this. Not very well. Perfect. I'm actually going to start with this guy here in green, and I'm going to do this. 6.63 times 10 to the negative 19th joules per one photon. Now, this is probably where I should have began. Each mole of something has how many pieces or parts? There we go, Avogadro's number, which the book likes to use this. There are 6.022 times 10 to the 23rd. A little bit different number than what we used here. Photons per one mole, yeah. Now our next issue is this. This is in joules, but in this given number here, it's in kilojoules, okay? So if I want to get rid of joules, and I say, all right, times, I take out the knife hand, J for joules, cancels down below, and then what we want is up top, how many joules are in a kilojoule? 1,000. So what I'll put down here is 1,000 joules per 1 kilojoules, and we'll turn to our calculations. Okay. So I start here with 6.63 times 10 to the negative 19th. Multiply it by Avogadro's number. I press enter, and then I divide by 1,000, and I end up with 399 kilojoules per mole. Okay, so 399 kilojoules per mole. Now, let's just think about what this is talking about. It needs at least 387 kilojoules per mole. With the value that was put into it, does it receive that much? Yeah, so since it receives that much, the bond can be broken. Okay, so you could put this, our oxygen bond can, oh, I should put bond maybe, bond can be broken because the amount of energy that we put into it is bigger than the amount of energy needed to break the bond. Again, I like to think of this as like breaking sticks. What's the minimum amount of force you need to put to break a stick? Well, we went over that, so our stick is broken, aka our bond. Questions? All right, last thing, and then we'll be done. Promise we'll be done by 9:30. Our Beer-Lambert law, which we talked about, and we'll get more into it as we go through this particular process here. The Beer-Lambert law is basically saying, hey, we dictate what the particular wavelength is, and we get this output of our result. Cool, great. It's shown by this formula, which we played around with, or I at least have identified or showed you with this. Our A is our absorbance value, which is what we got on our spectrometer, aka our calorimeter. The E is this constant here, or molar absorptivity. B is the path length, which is why we use that specific cuvette, that specific, typically they're 1 centimeter, and then C is that concentration. So that's how that machine actually was calculated. Okay. In our Beer-Lambert law here, okay, we are wanting to either find our concentration via using that absorbance value or vice versa, okay? Again, it's all a proportionality because the path length is going to stay the same. That fancy E symbol, again, also going to stay the same, all right? Okay. All right, so here we go. A student prepared 5 solutions of copper to sulfate. Hey, we did that. With different concentrations and then filled 5 cuvettes containing one of the solutions. Cuvettes were placed in the spectrometer. We used a calorimeter to set the appropriate wavelength for the maximum absorbance. Again, everything that we've done in the lab. The absorbance for each of the solutions was measured and recorded. The student plotted the absorbance versus concentration, very similar to what we did, as shown in the figure below. Which of the following is most likely explanation for the variance of our data for 0.6 molar copper to sulfate? So first off, 0.6, as we check this out, it is not in that straight line or that best fit line like we created in our lab there. Number 2, the absorbance level is a little bit more, okay, than it really should be, all right? So based on our options here, we have the cuvette, option A, the cuvette into which the 0.6 molar solution was placed had some water droplets inside. Probably not, because again, it's absorbing more. So if we are absorbing more, does it mean a higher or lower concentration? Higher, okay? So A is not a very good option because more water would technically dilute what's inside the vial. Option B, it says the cuvette into which the 0.6 molar solution was placed was filled slightly more than the other cuvettes. Again, it's the same substance, but we're just filling it above. Would that have any effect where that light's shining through? No, so B is not a good option either. C, the wavelength setting was accidentally moved away from the maximum absorbance. Well, if the maximum absorbance was moved away, shifted left or right, would we get a greater value of absorbance? No, it should dramatically drop down. So if that was the case, it would have to be below that straight fit line. So that leaves us with option D. The cuvette was used for the 0.6 molar solution, had not been wiped clean before putting the spectrometer in there. Okay, we talked about fingerprints. That fingerprint may not seem like a whole lot or a whole big deal, but those fingerprints absorb some of that light, thus affecting the actual true concentration. So D would be your best example there, or best fit for this question. Questions? All right, so our free response here, and somebody correct me if I'm wrong, this is the last part of this, right? Sweet. All right, so we have a spectrometer. It was used to determine the percent of cobalt in ore containing cobalt and some inert materials with known cobalt 2+. They're prepared and the absorbance of each of the solutions is measured at a wavelength of optimum absorbance. The data was used to create the calibration plot as shown below. Okay, so it says a 0.389 sample of the ore is completely dissolved in concentrated nitric acid. The mixture is diluted with water to a final volume of 25 milliliters. Assume that all the cobalt in the ore sample is converted to cobalt 2 plus. Cool. We want to know what is the concentration of cobalt 2 plus in the solution if the absorbance sample of the solution is 0.45. Okay, so we're going to start with each of these. Each of these would be a question. This would most likely be a longer free response question. But we start here with that value of our 0.45. Okay, if we have an absorbance of 0.45, what it wants us to do is it wants us to utilize this chart. And again, 0.45 would be right here. We mark in green. And it would be, I'm going to show it with this dot, right here on this line. So the first thing is this. All we have to do is read down, and it says, okay, 0.45. We find it here on the y-axis. We go all the way down to the x-axis, and our concentration is 0.08. Okay, so our cobalt 2 plus, I guess I probably shouldn't put carbon monoxide, but how about cobalt 2 plus, is equal to 0.08 molar of our value. Okay. Now we want to calculate the number of moles of cobalt 2 plus in the 25 milliliters of our solution. Okay. So now let's think about this. We have our concentration and we have our volume. What formula could we use to find out the specific number of moles of cobalt 2 plus in our 25 ml solution? For the second part, we got big M. What does big M mean? Molarity. Okay, so now big M equals what divided by what? There we go. Moles over liters. Okay, and so now what we can do is this. We know our molarity is 0.08. Okay, so I'm just going to plug this in and say 0.08 big M equals, I don't know how many moles of our substance, all divided by not 25, but what's 25 divided by 1,000? Yep, 0.025 liters. And so that's what I'm going to put, 0.025 liters. Okay, so all we got to do on this one is take our calculators and go 0.08 times 0.025, and I get a value in moles of 0.002 moles of our cobalt 2 plus. Okay. Questions on that before we go to that last bullet there? Okay. So our last value here is this. We want to be able to calculate the mass percent of cobalt in our 0.389 sample. Okay. 0.389 grams, it's not a pure substance. There's some cobalt, but there's some other stuff in it. So we want to know how many moles of cobalt are in there. What is the percentage? So what we need to do is this. I'm going to start out with my 0.002 moles of cobalt 2 plus, and I'm going to put it down here. I'm going to say 0.002 moles of our cobalt 2 plus, and I'm going to convert it to grams. Now, if I take out my knife hand and go like this, what unit has to cancel diagonal? Moles of that cobalt 2 plus. Oh, I meant to go to yellow. Moles of our CO2 plus, and on top we can go to grams of cobalt 2 plus. Now, gram over mole or mole over gram of one element, where would I find that info? periodic table. Now I'm just going to give it to you. The molar mass is 58.93 grams per 1 mole. So that's 58.93 grams per that 1 mole. And so my 0.002, I'm just going to multiply by 58.93, and I get a value in grams of 0.118 grams there. Of cobalt 2 plus, and all we would have to do is divide that by our value of 0.389 of our total value, and to express it as a percent, what do we have to do at the end here? Too easy. Okay, so I take 0.118 divided by 0.389. I get 0.30, number keeps going out, and then multiply by 100, and our value here is 30.3% cobalt 2 plus. All right, too easy. Oh, just missed 9:30. Uh-oh.
It went to the student